we're going to talk about confidence intervals and hypothesis testing for the difference of two paired means. Okay, so we've been talking about independent samples so far. One sample, two independent samples. Now we're going to talk about paired samples. So we're going to look at the difference between independent samples and paired samples. We're also going to try and clarify the difference between independent samples and independent variables, because paired samples still use independent variables. Then we're going to talk about two types of t-tests. One that we've covered so far, or also called hypothesis testing. One that we've covered so far with independent samples, and the new one that we're going to cover with paired samples. Then we're going to introduce some notation for paired samples, go through the steps of hypothesis testing for paired samples, and adjust, or actually add on to the rules of the SDOD that we've already been looking at, adding on paired samples rules. Finally, we're going to go over the formulas that go with the steps of hypothesis testing for independent as well as paired samples. And finally, we're just going to briefly cover confidence intervals for paired samples. Okay, so here's the goal of hypothesis testing. Remember, with one sample, our goal was to reject the null when we get a sample that's significantly different from the hypothesized population. And when we talk about two-tailed hypotheses, we're really saying the hypothesized population might be significantly higher or significantly lower. Either way, we don't care. So the sample is too low or it's too high. It's too extreme in some way. And if that's the case, we reject the null. In two samples, what we do is we reject the null when we get samples that are significantly different from each other in some way. Either one is significantly lower than the other, or the other is significantly lower than the one, right? So it doesn't matter. And so our null hypothesis becomes this idea that x minus y either equals 0 because they're the same, and the alternative is that it doesn't equal 0 because they're different from each other, right? So if they're the same, that's considered the null hypotheses, and when they're different, that's considered the alternative hypotheses. Remember, another way you could write this is by adding y to each side, and then you get x equals y, right? X equals y, they're the same, right? So, so in that way, you know that you're covering the entire space of all the differences, and at the end of the day, we can figure out whether they're whether they're the same, or whether we do not think they're the same. Okay. Now let's talk about independent samples versus paired samples, because from here on out, we're totally going to be dealing with paired samples. It would help to know what the heck those are, right? So independent samples, the scores are derived separately from each other. For instance, they came from separate people, separate schools, separate petri dishes, right? So the samples are independent from each other. My getting of this sample had nothing to do with my getting of this other sample. In dependent, another word for paired, right? In dependent or paired samples, the scores are linked in some way. For instance, they're linked by the same person, right? So my score on the math test and my score on the English test, right? They're linked because they both come from me. Maybe married couple. Maybe you ask one married couple, how many children would you like, you ask one spouse, how many children would you like to have, and you ask the other spouse, how many children would you like to have, right? So in that way, although they come from different people, these scores are linked because they come from the same married couple. Or another thing might be a pre and post test of a class, right? So maybe a statistics class might do a pre and post test. So maybe 10 different statistics classes from all over the United States get picked to do a pre and post test. And those tests are linked because the same class did the first test and the second test, right? And 10 different classes did the pairs, right? So in that way, they're paired samples, right? So it's not just a hodgepodge of pretest scores and a hodgepodge of post-test scores. It's more like a neat line where the pretest scores for this guy, for this class, is lined up with the pretest scores for that class, right? And they're all lined up next to each other. Okay, so now that you know the sort of technical definitions, let's see if we could pick them out. So which of these is which? So the test scores from Professor X's class versus test scores from Professor Y's class. Well, these count as independent samples because they just come from different classes. They're not, each score is not linked in any particular way. River samples from 8 feet deep versus 16 feet deep. Well, this also doesn't really seem like paired samples unless they went through some procedure to make sure it's the same spot in the river. But barring that, it's probably an independent samples. Male heights versus female heights. They're just a jumble of heights over here and a jumble of heights over here. They're not like matched to each other. So I would say independent samples. Left-hand span versus right-hand span. Well, in this case, usually these two spans come from the same person. It's not a hodgepodge here and a hodgepodge here. It's like left hand, right hand from person 1, left hand, right hand from person 2, left hand, right hand from person 3. So I would say this is a paired sample. Productive vocabulary of 2-year-old infants who have been raised by bilingual parents versus monolingual parents. Again, I would say it's a bunch of scores here and a bunch of scores here. They're not lined up in any way. So I would say independent. Productive vocabulary of identical twins. Twin 1, twin 2, twin 1, twin 2, twin 1, twin 2. Here we see paired samples. Scores on an eye gaze task by autistic individuals and age-matched controls. So autistic individuals often have trouble with eye gaze, but in order to know that, you would have to match them with people who are the same age who are not autistic, right? And so here we have autistic individuals lined up with somebody who's their same age who's not autistic, right? So there are these nice even pairs, and each pair has eye gaze scores, right? And so I would say these are paired samples. So hopefully that gives you a better idea of some examples of paired samples. Okay, so what about independent samples versus independent variables, what you'll also see as IV? Well, in multi-sample statistics, like 2-sample, 3-sample, 4-sample, we're often trying to find some sort of predictive relationship between the IV and the DV, the independent variable and the dependent variable. Usually this is often called the test or the score, right? The independent variable is sort of seen as the predictor, and the dependent variable is the thing that's being predicted, the outcome, right? So, for instance, we might be interested in the IV of parent language. Oops. And that might be, you might have 2 levels, bilingual and monolingual. Right? And you might be interested in how that impacts the DV of children's vocabulary. Right? So here we sort of have these 2 groups, bilingual and monolingual. Right? And we have all these scores from children. And these are independent samples because although we have 2 groups, these scores aren't linked to each other in any particular way. They're just a hodgepodge of scores here and a hodgepodge of scores here. On the other hand, if our IV is something like, let's say, older versus young, so age of twin, and we have, slightly older by like a couple minutes or seconds and younger, right? And we want to know if that has an impact, so coming out order, has an impact on vocabulary, right? We'll have a bunch of scores for older twins versus younger twins, right? But these scores are not just in a jumble. They're linked to each other because these are twins, right? They're genetically identical, right? So this is sort of the picture you could draw. And so the IV really tells you how you determine these groups. The paired part tells you whether these groups scores are linked to some scores in the other group for some reason or another, right? Here they are linked. Here they're not linked, right? Okay, so in all t-tests, so far we've been calling them hypothesis testing, right? We're going to have other hypothesis tests that don't use t-tests, but so far we've been using t-tests. T-tests always have some sort of categorical IV so that you could create different groups. And in t-tests, it's always technically two groups, two means, paired means. And the DV is always continuous. And the reason that the dependent variable or the score is always continuous is because you need to calculate means in order to do a t-test, right? Because we're comparing means to and looking at standard error, and you can't compute mean and standard error for categorical variables. So if you have a categorical variable such as, yes or no, you can't quite compute a mean for that, right? Or if you have a categorical variable like red or yellow, you can't compute a standard error for that. If you did have a categorical DV and a categorical IV, you would use what's called a logistic test, but we're actually not going to cover that. That doesn't usually get covered in descriptive and inferential statistics. Okay. Usually have to do like either graduate level work or higher level statistics courses. Okay, so there's really two types of t-tests given all of this. Remember, all t-tests have this. This is all t-tests, right? So both of these t-tests are going to use categorical IVs and continuous DVs. The first kind of t-test is what we've been talking about so far. Independent samples t-test. The second type is what we're going to cover today, called paired or dependent samples t-test. Both of these have categorical IVs and continuous DVs. Now let's talk about some notations for paired samples. Just like before with two sample independent samples t-tests, for one sample you might call it X so that its individual members are X sub 1, X sub 2, X sub 3. And remember, each sample is a set of numbers. It's not just one number. It's a set of numbers. A second sample you might call Y. I didn't have to pick X and Y, though. I could have picked two other letters, X and Y. And Y could just mean another sample, right? You could have picked W or B or N, right? We usually try to reserve N, T, F, D. We try to reserve a couple of these letters, K, for other things in statistics, but it's mostly by culture more than like we have to do it by rules. Okay. Here's the third thing you need to know for paired samples. With paired samples, remember, X sub 1 and Y sub 1 are somehow linked to each other. They either come from the same person or the same married couple, or they're a set of twins, or it's an autistic person and an age match control, right? So there's all these reasons why these are linked to each other in some way. And because of that, you could actually subtract these scores from each other and get a set of different scores. And that's what we call D. So D is X sub 1 minus Y sub 1. So what is the difference between these two guys, these two scores? What is the difference between these two scores? And what is the difference between these two scores? So these are paired differences. Now, let's think about this. If the mean of x is denoted as x bar and the mean of y is denoted as y bar, what do you think the mean of d might be? Well, if you guess d bar, that's a good guess because that's what it is. So if you got the mean of this entire set, that would be d bar. Okay, so once you have d bar, now what you could do is imagine having a sampling distribution made of d bars, right? Sampling distribution of d bars, right? So it's not x bars anymore, sampling distribution of the mean. It's the sampling distribution of the mean of a whole bunch of differences. So that's sort of a new idea here. So imagine getting a whole bunch of getting a sample of D's, calculating the mean, D bar, and placing it somewhere here. You will get a distribution, a sampling distribution of D bars, right? And that's what we're going to learn about next. These are means of a bunch of linked differences. Okay, so when we go through the steps of hypothesis testing for paired samples, it's going to be very similar to hypothesis testing for independent samples, with just a few tweaks. So first, you need to state a hypothesis. And often our null hypothesis is that the two groups of scores, the two samples, x and y, they're the same. So, so usually that's the null hypothesis. Then you pick a significance level, just like before. How weird does our sample have to be for us to reject that null hypothesis? Then we set a decision stage, and we draw the S dot D bar, right? And we identify the critical limits and rejection regions, and we find the critical test statistic. From here on out, I'm just going to assume, as most problems assume, that you're almost never going to be given the actual standard deviation of the population. So from here on out, I'm usually going to be using T instead of Z. Then we use sample differences, the actual samples differences, and S dot in order to compute the mean differences. So now we're not dealing with just with means, we're dealing with mean differences, test statistic, and p-value. And then we compare the sample to the population, and we decide whether to reject the null or not. So things are very, very similar so far, but it really is going to make us figure out what S dot, this new S dot, is all about.